Welcome back to Think Design Work Smart. I'm Alex Bolboaca and I'm coming at you from the Mozaic Works studios. And what I have for you today is a deeper insight, a deeper conversation around object-oriented programming. I've been saying a number of times on this channel in the past that object-oriented programming is different from what we're practicing, because what most of us are practicing in Java, C#, C++ is class-oriented programming. And therefore, I'd like to show you an alternative, and I have to tell you this time the presentation and this video will have code, so we'll have to look at code. In case you are listening, I will try to explain the code, but it's still better if you can watch this time. I encourage people to listen, and we try to make all the videos easy to listen as well. In this case, it's a bit more difficult to do so. Anyway, another few things that I'd like to talk about before we start. First of all, I posted a question regarding secure coding. Do you have any questions about secure coding? Let us know. It's something that we are working on. We have a learning program on this, and I would like to answer more questions and see what other challenges people are facing with this and make videos about those. I think it's a very important topic, and if you are puzzled about secure coding, if you have no idea what it means, or if you have specific questions, by all means let us know. I'd be happy to make videos and answer them. Second thing, we publish videos weekly, every Saturday usually, at least weekly. Sometimes we add some extra videos, but you can count on weekly videos, so stay tuned. Come back every week. We'd like to have more contacts with you, the community, since the community has now grown. We are about 612 followers at the point of this recording, and so it's very cool if we could collaborate a bit more and, you know, ask us questions. I'd love to. My favorite thing is to answer this. Anyway, enough about this. Time to go to some code. So let's talk a bit about object-oriented programming. And let's think about what object-oriented programming means for most of us. And if I were to tell you the things that I've learned about object-oriented programming, I had a period when I was trying to understand precisely what it means. And so I got my hands on all the books I could find on object-oriented programming, and all of them had a few similarities. The first one is how they defined object-oriented programming, which was that the fundamental characteristics of objects are encapsulation, inheritance, and polymorphism. Encapsulation means that we have the data with the behavior in the same construct. Inheritance means that we can replicate parts of the construct from another object. And polymorphism means that we can, particularly with inheritance, because this is the type of polymorphism that we know, we can call the same method on different objects, and they would do different things, well, slightly different things, depending on the object we call it upon. But in order to do so, most of the times you needed inheritance. So these are the three characteristics, but strangely enough, the first thing that happens after that is we start learning about how to define an object. And how do we define an object? Well, we write a class, right? And this is where the things start getting muddy for me, because if we are really doing object-oriented programming, why aren't we defining objects and instead we are defining classes? And in discussions later on with people who have been in the beginning of object-oriented programming, like Rebecca Worfs-Brock, I noticed something very interesting. She was first thinking about objects and then about how to classify those objects into classes, because classes, what classes fundamentally are, as their name is saying, is a classification of objects. So you basically have two ways of thinking about a problem with, or if you're trying to do object-oriented programming. One way is to start from, this is the problem and let's figure out the classes, you know? And this is what we used to do for a very long time. Like say, okay, so we'll have a class window, and then from that class window, we will have different implementations. One of them is a dialogue, one of them is a model dialogue, and so on. And you'll have a bunch of implementations like this. Or typically you'd have, let's say, a dialogue, and then that will have another implementation, one that is a model dialogue, and all these things. So basically started with the classification before having the objects. And that is not the best way of thinking about it, I believe. And based on my practice and experience, I don't think it's the right way. Fortunately, domain-driven design came along and it pushed the needle kind of in the other direction. And we are now thinking more about still classes, but kind of more about objects. So it's a little bit better. But the question is, how would a system look in which we start thinking about objects and then classify them? That's the interesting question. And one thing that is bugging me is that you have to write a class in order to do that. So let's look at another thing that I've learned. This is something I learned via J.B. Reinsberger, but somebody else told it, and I don't remember, unfortunately, who did, but if you know, please let me know. I like to give the proper credit. That fundamentally, and this is gonna sound a bit weird, what an object is a collection of functions that are partially applied and that have some cohesion between them. So functions that work well together, and the partial application is about the data that is common. Okay, we'll have to unpack this, and the best way to unpack this is through an example. First of all, we have to understand what partial application is, and this is what we will do. All right, let me show you the screen, and I have a simple test here. The test says assert 4 = 5. Very good test to write, because I can run it. I can see that my testing framework is working. And now if I have assert 4 = 4, I can run it and everything is green. Perfect. Now let's start by doing something that is normal, let's say, something that we would normally do. The second thing that most object-oriented programming books did was to define classes that are related in some way with geometric primitives, like lines, squares, segments. Well, usually not segments. They found that too difficult, I guess. But usually it was square, polygon, things like that. So let's look at a square for now. Okay, so we'll have a class square. I'm writing in Python, by the way. So Yeah. And what I will have is a constructor, and I'm gonna pass in a size, and I'm gonna say self.size equals size, and I'm gonna compute an area, return self.size times self.size, and I'm gonna replace that with test square area, and I'm gonna say 25 equals square of 5 dot area. Okay. All right. Let's run this, and it tells me, yeah, that's fine. Just to see that things are working. I'm not doing TDD, by the way. This is just I'll show an example, but I'm gonna use the tests for examples. All right. So what we've done here is we've written a class square that has an area. It's kind of the normal thing. What else might we have? We might have get size, although this is kind of silly. And let's do it the way I like it. Return self.size, and because of this I will have to rename this to self dot. I'll use 2 underlines. This is a convention in Python. It tells us that thing is, there are no private things in classes in Python, but this assumes that this tells the user of the class square that if you're trying to use underscore size, it's on you, because it might change. So square of 5 dot size should give me 5, because it just returns the size. And maybe the size, okay, maybe size is not a good name. It's probably gonna be side length or something like that, but let's go with it. All right, now let's look at what would it mean to have this class in a different way. So we need a square object, and let's say I'm gonna focus on the area function for now. The area function uses this size thing. So how about I'm gonna write it like this. Def square area of size, return size times size. No semicolon, because I am in Python, and that's one of the perks. I don't have to use semicolons. Assert 25 equals square area of 5. Perfect. Tests are passing. And now here's where the interesting thing comes in. I can do something called a partial application, and I can do it in 2 ways. So partial application would mean I want a function, area of square with length with size 5, and I want this to be a function, and I'm gonna do lambda square area of 5, and okay, let's this down a little bit. No, I don't want it to be a def. I don't have a no, I want to have a lambda square area. Okay, and this is equal. Okay, and now I can do assert 25 equals area of square with side. Come on. So this is okay. Assert 20 area of square with size 5 of nothing. All right. What I have done is a partial application. This is what partial application means. I have now bound the number 5 to square area. And what I've got is a new function, which keeps wanting me to do differently, but I don't want to do it like he wants me to do. Okay, Visual Studio, stop helping me. Stop helping me. VS Code. All right. I'm gonna have to change the setting because that will bug me. So short break while I will change this setting to make sure that everything is working fine. All right, and I'm back. I found out that the simplest way is to use parentheses here. So we'll use parentheses to define our lambdas. All right. So where I was is I was defining this partial application. And before we move forward, let me show you another way of using partial application. We can do import functools.partial. And we will do area of square with size 5 using functools equals partial of square area and 5, and then we will do the same thing only with this new function. I think from functools import partial. Let me quickly check. From functools, yeah. From functools, import partial. All right. So now what we have is a partial application. Cool. Now this is not very surprising, let's say. It just shows the fundamentals of partial functional application. And basically what it shows us is that we could have a square. Let me do this instead. We could have a def square of size that returns a dictionary where we have area going to square to a lambda that goes to square area of size. And if we really want to, we can have a size that goes to lambda lambda, yeah, just size. And I need a comma. And now what I can do is square of 5 of size dot, well, call it, and assert that 25 is, and we don't want size, we want area, and 2 equals here. What has this shown us? It has shown us that we can make an object without actually having a class, right? The class is only the structure behind the thing. But this object is formed from two things, which are two functions that are partially applied. And by partially applied or bound, one of the parameters is bound to a value. Okay? And this might not look like very interesting thing, and definitely the syntax is not that nice and so on. But let's go a little bit further in our exploration. I'm gonna use a class that I found on Stack Overflow that is called actually it was called .dict initially, but I renamed it to an object, and this class will do something interesting. It takes a dictionary and it basically overrides the functions for get attribute, set attribute, delete attribute. It just allows us to do our normal dot notation instead of having the dictionary obvious, right? So now suddenly with this change, what is the difference between this last line, assert 25 equals square of 5 dot area, and the first line, assert 25 equals square of 5 dot area? The first one uses a class, but the second one uses a collection of partially applied functions. Okay? And basically what we have here is an object, right? This is, okay, it's not probably something that you want to use in production, and I'm going to preface this for everything. This is just a way of thinking differently and forcing you to think about objects rather than classes, because this is what fundamentally objects are. And maybe we can make it even more interesting. But before that, let us look at something interesting. This function is a function that receives a parameter size and then returns the same parameter. So what this should be is identity of value, return value. And then what we can do is to do a partial application of identity of size. All right. How about this for polymorphism? This is one thing that I find really funny. We are talking about polymorphism in the context of classes. But look at this. This is almost the ultimate polymorphic function. It doesn't care what you are passing in, it just returns it. This can be any type. It can be an int, it can be a float, it can be anything you want. It can be a complex type, it can be a simple type, it doesn't matter. It will just return that value. It's fundamentally the most polymorphic function you can think about, because nothing will make it unhinged, let's say. So this has shown us the equivalence between an object and a set of partially applied functions. So, and this shows us that we can go further into or think differently about objects. Start thinking about objects before writing a single class statement. I never write a class statement here. And okay, you might say that this is a class. And yeah, that's basically what it is. But it's nice to have different perspectives from time to time and look at things from another vantage point and think about these as objects. But now let's do something slightly more or slightly different. And what I was thinking is, how about we do a bit of temperature computations and conversions? Everybody loves temperatures, of course. I have here a few functions. I'm going to copy them. And yeah, let's go here. So what do we have here? We have Fahrenheit to Celsius, Celsius to Fahrenheit, Celsius format, Fahrenheit format. And let's write a few quick tests for them. Tests. Let's actually do test Celsius. Okay. Assert. I don't remember the exact numbers, but I think 38 will be equals to Fahrenheit to Celsius 100. Assert 38 degrees. No. 38. Yeah, you just need the degree. Degree Celsius equals Celsius format of 38. And now let's run make, and apparently I did it. Let's try 39 here just to make sure that the tests are running. Yeah, all right. No, yeah, that has to be 38 and the tests again. Cool. So, and the reason why it's 38 is because this is rounding. It's just to keep things simple. Okay. And now let's do the same for Fahrenheit. Copy 3 lines, paste, test Fahrenheit, and this will be Celsius to Fahrenheit of 38 should be 100, and then we'll have 100F, which is Fahrenheit format of 100. All right, cool. So these functions are working. How about we try to combine them into something? Okay. What might that something be? Well, I'm thinking about combining them into, let's start with Celsius temperature. Celsius temperature equals an object of, and what do we need here? We need format, which will be lambda of Celsius temperature. Okay, I'm gonna need a function. Def Celsius temperature of value. And this will return an object of lambda Celsius temperature of value. Cool. And we're gonna no, not what am I doing? Celsius format. And I'm gonna need convert that is a lambda Celsius to Fahrenheit of value. And an object, I need some extra parentheses here. And now what I can do is to say assert 38 equals Celsius temperature of 100 Celsius, yeah, of 100 dot convert. And normally I should, oh, what have we done wrong? Convert, it's Fahrenheit. Wait a minute, Celsius temperature of 38, yeah. And this should be 100. Okay. Now, the next thing is formatting. So Celsius temperature of 38 format. All right, run the tests. Everything is working fine. And let's do the same things, but with Fahrenheit. Fahrenheit. I haven't actually implemented Fahrenheit temperature, so format will be Fahrenheit format. This should be Fahrenheit to Celsius. And now we can do Fahrenheit temperature of 100, convert equals 38, and this will be 100 F equals Fahrenheit temperature of 100 dot format. Right. Cool. So now we have this thing, okay? We have Celsius temperature, Fahrenheit temperature. These are basically two objects. Now let's make things a bit more interesting. Instead of returning this, let's return Celsius temperature of Fahrenheit to Celsius value, and this will be Fahrenheit temperature of Celsius to Fahrenheit value. Because conversion will give me the other thing. Instead of getting this, I can do convert dot format, and this should be 100F. If I'm running the tests right now, I should get an error here because this should be 300 degrees. Copy to characters, paste. Okay, I copied 3 characters. And this should be, oh no, and format. Cool. And in case I want to have the value would be lambda identity of value. And I would have value is lambda identity of value. In case I want to get the value here instead of doing all that, so maybe I want to have 38 equals convert value. Cool. And we can do the same thing. 100 equals Celsius, convert dot value. So now we have an object that returns another object. Celsius, when converts to Fahrenheit, returns Fahrenheit object, and so on. And now here's the final thing that I like to show you, because this is a slightly more interesting example. But here's where it might become interesting. We notice that these classes have kind of the same thing. So how about we make a prototype? And I'm gonna copy from my previous code just so that I don't have to do anything. I have created a temperature prototype that has a value, has a unit, has a convert lambda, and has a formatting lambda. Okay, let's call this format. And format lambda. Okay. And the value will basically use, in this case I'm using partial, so it will be a partial application of identity to either the value or the unit. And then converting is a convert lambda, format is a format lambda. And so what I could do is return a temperature prototype that has a value, has a unit, which is Celsius, has a convert lambda, which is let's put these on the same line, and then let's copy these 2 lines. And just to make things easier, we'll do value equals value, unit equals Celsius, convert lambda equals this lambda, and format lambda equals this lambda. Remove this, comma, do this. Let's try to run the tests. If we made any mistakes, no mistakes. We can remove this last part, and now we have a temperature prototype, and now we can do kind of the same thing with Fahrenheit temperature, which is value, unit, convert lambda. This will be Celsius temperature, Fahrenheit, Fahrenheit, oh come on, Fahrenheit to Celsius. I keep hitting the wrong buttons. And this is the Fahrenheit format. And let's run the tests again. No mistakes. I think we have, okay, 5 lines, not 4. Cool. Make, run. Okay. So now we have a temperature prototype, which is fundamentally, let's say, the structure behind the class. Only now you can define any kind of temperature. It's more like a base class than anything else, but it's almost more polymorphic than that. It has more power. Now I have one last thing that I like to show you. Let's say we want to create a more generic temperature class. So we have a temperature that gets a value and the unit can be Celsius or Fahrenheit, or, and in this case, it can be something that doesn't match any of those. So let's try to write a simple test here. Assert 38 equals Fahrenheit, temperature of 100 and unit is Fahrenheit, dot convert, or okay, let's just get the value instead of doing all that thing. So we'll have 100 equals this. Fahrenheit temperature from prototype is not defined. Okay, because I just changed the things. So we can just replace those. All right, make, cool. And the last thing will be, let's check if this is working for Celsius as well. So temperature of 138 and Celsius dot value. Or maybe if we want to, let's do format so that we are more convinced it is doing the right thing. And then you do 100 F equals temperature dot format. Cool, run, perfect. So things are still working. Now what's with the dummy temperature? That's an interesting one. What would we do in case we are passing the wrong unit here? Like we are passing G. There are a few things we can do. I'm just gonna write temperature of 100 Gs. And this should be a number, okay. If I'm running this right now, it will give me an error. But basically I could throw here an error, or I can do the nullable pattern, nullable object pattern, which is, how about we define a dummy temperature object that takes a value in the unit and that uses the value, says the unit to something like not available, NA, doesn't exist. Let's do n/a just. And then If we are trying to convert it, it will return the same value. And if we are trying to format, it will just say, look, you have a bed temperature unit and the unit is G. Let's see how this works. So we'll have this. Now we can do assert 100 equals temperature dot value. Okay, it is 100. We can do assert, what is the text here? Bed temperature unit G is equal with temperature of 100G format. And in case we want to convert it, we'll have assert bed temperature unit G equals with temperature dot convert dot format. Hey, come on. Format. Let's see. Hey. So, and this shows a few things that are interesting here. One is structural pattern matching that you can do now in Python starting with 3.10. And this, okay, I'm just matching units here, but you can match a lot more interesting things. And finally, what it shows is how easy it is to do a dummy, it's a nullable object pattern, right? It's an object that looks like a temperature, but actually works differently. And how easy it is to write a dummy temperature object, which basically returns the same thing. All right, this is what I wanted to show you. I showed you first how objects are actually equivalent with a collection of partially applied functions that hopefully are also cohesive, so they have a connection with each other. I also showed you how we can extract a prototype. I showed you how polymorphism is actually much, much better at the level of functions often than at the level of classes. And what I hope I've shown you, I don't think anyone will use this in production as their way of writing code, although I have to say it looks very similar with JavaScript, so JavaScript most likely can use something like that. But in case you're doing something like Java, C#, C++, Python, I don't expect you to use these kind of constructs. But what I hope that I've done is to prove to you that objects are different from classes. And that you can actually do object-oriented programming if you just think about, I need an object. And okay, maybe you need to write a class in order to get an object. But how about start thinking about the objects that you need instead of thinking about the classes that you need? Okay, this was the main point of this demonstration. I hope you found this interesting, intriguing, maybe helpful, I hope. Either way, remember that we have, and I will keep sending questions to you and waiting for comments from you. I really can use your questions in order to actually have a conversation with you. And if you want more live videos, more coding like this, let me know. If you want live videos, yeah, we can definitely do that as well. And remember that we have a new video every week. Keep posted. And thank you kindly for the view. And until next time, remember to think, design, and work smart.